Okay, welcome in the week 7 of our calculus class. And in this session, I will finish chapter 3. Before I start chapter 3, of course, I have a quick announcement, as always. We probably realize that this is the last week before the second midterm. That means next week will be the midterm review, and the midterm will be open on Thursday. That means make sure that you have your examity appointment, examity time spot booked, because the last minute booking is not really recommended and it's stressful. Also, taking the test at examity, make sure that you have a nice quiet room, like nice and clean room, clean desk. Leave all of your electronics, books and notes outside the room, lock the room and take your test. Then you will see how less stressful it will be. Okay? That's the technical things. And of course, I want you to be ready and prepared, because I would like everybody to succeed, and I would like to do everything for you to be successful. And I did recommend this, but I will repeat one more time. I will even start today, or let's say this week, to review for your midterm. I did post lots of sample tests on Canvas in the module, I believe the week 8, because that's the exam week. And what I will recommend, please print the sample test, okay? And the same thing, lock yourself in the nice clean room, time yourself, like set up a timer, 90 minutes. Please, do not have any notes, books, electronics in your room, and try to take that sample test. Okay, not checking the solution in the meantime. I mean, during taking the test. Do not make any breaks, and even the bathroom breaks, try to plan accordingly. And then taking the test, after 90 minutes, you can check the solution against mine, which I posted on Canvas too. Okay? And then you will see the result will be the real reflection of your knowledge, of your readiness. And then I think I have 5 or 6 sample tests. And I can guarantee you that if you can score in the real examination settings, if you can score more than 90%, you will score the same thing on your midterm. Okay, that means please remember, try to create exactly the same real situation, real settings, real exam settings, and take the test. Do not check any books, any notes taking the test. Don't make any breaks, and set up the time. Of course, time is the also important component. Okay? And you can take, I think I posted 5 or 6 sample tests, and then you can repeat. Okay? If you run out of the test, you can even take the same test again. This way you will practice the concept, which is for the exam too, and you will see how confident you will be at your real test. Okay, that's my suggestion. Okay, before I start, because talk a little bit about, we can see this topic, limits at infinity and horizontal asymptotes, because this is a few things that we will need to graph a function. Because the main wrapping up topic for chapter 3 is graphing a function, but we're still missing a few things. And also a big thing for this week is the optimization. And another announcement, you probably noticed that this week I posted the normal week 7 module, and I actually pull out section 3.7, which is the optimization, and I did create extra credit module. That means this is still important, and optimization will be on your midterm and the final test. However, for this week, if you will take extra self-assessment and extra weekly quiz, you will have extra points, extra credits. Okay, That means you probably noticed this. That means you kind of have 2 self-assessments quizzes and 2 weekly quizzes, but the second set is for extra credit. That means 10 plus 3, 13 extra points. Okay? That means it's worth it. Any point is always worth it. Okay, that means let's start. What I will do, I will switch the camera because then the internet works a little bit better. Okay, that means I'm still there. Before I start, actually, I do have, I have one question. I mean, I have 2, but let's solve at least this one. Okay, this is still from chapter 6. You have similar question, but let me just double check that we understand before the second test and of course for the final. That means let's solve this problem. The graph of the first derivative f prime of continuous function f is given. Okay, and we can see that's the graph. And we have 3 questions. On what intervals the function, intervals is f increase? That means having a derivative, we know that if the derivative is positive, function is increasing. If the derivative is negative, function is decreasing. That's what I will do. And since this is the derivative, underneath, I will draw just the x, the number line, and I will test the sign of the derivative. And we can see this is the zeros are -5, -1, to, let's say 2.5, and then 5. And yes, 6 is interesting number. 6 is not really, derivative is actually undefined, but we also know if the derivative is undefined at the number, it is the critical point, especially that we know that function is continuous function everywhere. That means function is defined everywhere. Okay, and then 7. That's the zeros of the derivative. And now let's see, between -infinity and -5, I can move this a little bit. Between -infinity and -5, function, the derivative is below, that means it's negative. Then derivative is above, then it's positive. Because above the x-axis, the values are positive. Below are negative. And again, I can, that's again below, that means everything up to this is negative. And then from 5 to 6, that's actually positive. And from 7 to 10 is also positive. But between 6 and 7 is negative. Okay, that we do have the sign of the derivative, and that's almost everything what we need. Then function is decreasing, increasing, decreasing, still decreasing, increasing, decreasing, increasing. Okay? And we know what this means. At -5, function attains local minimum. At -1, local maximum. At 2.5, actually nothing, because function is decreasing and again decreasing. And at 5 is local minimum. I can actually write maximum here, local minimum here. At 6, this is interesting. Yes, we shouldn't miss 6, because we can see on the left-hand side, derivative is positive, on the right-hand side, derivative is negative. That means function is changing sign from positive to negative, maximum. And at 7 is minimum. Okay? That means that's important to do the test and read take the conclusion. Okay? That means we do have the intervals of increase. Of course, this will be the blue one, from -5 to -1, from 5 to 6, and from 7 to, let's say, to 10. Okay? And then part B is asking for local maximum, local minimum. That's when we do have maximum, -1 and 6, at -1 and 6, minimum at -5, 5 and 7. And we also have a question for the second derivative. Okay, we can see what are x coordinates of inflection points. Okay? That's when we remember inflection points, like potential inflection points, are the points where the second derivative is 0. Which means if I look at this graph as a function, let's say that, I mean, this is derivative, I know, but this is that, looking at this graph, I will see that this graph, that means this has nothing to do with the function, what I'm saying now, but this graph is increasing. We can see it, I can even add different color, maybe green. It's increasing from negative infinity to negative 3, okay? And then it's decreasing. That means if this graph is increasing, its derivative is positive. And since this is the derivative, then its derivative will be the second derivative. That means second derivative is positive if that graph increases. Okay? And it is increasing. And then, of course, the second derivative is negative. Second derivative is negative if this is decreasing. That we can see all of these local extreme values for the derivative. I'm not talking about these red dots. That's the zeros of the derivative. That's different. Okay. Now I am actually talking about the extreme values. Right? The green dots. All of the green dots. Because we can see function is increasing, decreasing, the second derivative will be positive, negative, since this is the first derivative. That means this is the point that original function will have inflection point, because the second derivative will be 0. At this point, second derivative is definitely 0, and the second derivative is changing the sign. That means inflection points are for the function at negative 3. The same will happen, I believe this is 1, and the same will actually happen at 2.5, and at 4, and, no, I don't know, 9. Okay, 6 is not really, actually, let's see if 6 is the inflection point, because 6 is a weird number. The first derivative is not defined, but we may still have an inflection point. Function is, I mean, this graph, I don't want to call function. This graph is increasing, actually increasing. This means the second derivative is positive because it's the derivative of the derivative. And on the right-hand side, oh, okay, it's also increasing. Okay, that means no. If it's positive and positive on both sides, that means this number 6 will be not an inflection point. Because this, if the second derivative is positive, function is concave up and then again concave up. Okay, that means 6 is not really an inflection point. Okay, that's when we can see it's important exercise, because from the derivative, the graph of the derivative, we're reading lots of information about the function. Okay. And I do have somebody ask me, I think, this question. Okay, that's me. Let's see quickly. We can find how many points of inflection does the graph of the function f have if the second derivative is defined this way. That means it's a really nice way because we see the zeros right away, and I'm assuming that function is continuous function. That means all of the numbers are in the domain. That means I can see that the second derivative is 0 if and only if, and we can see if x is 0, because that's from the 0 from this, -1 from this, and -2 from this. Because if I substitute 0, -1, and -2, I'm getting 0. Okay, and I will put this on the number line. -1, 0, actually, -2. -1 and 0, and let's test the second derivative. Because even if the second derivative is 0, not necessary all of the points will be the inflection points, right? We remember, we have to have different sign on both sides. Okay, let's pick the test value -3. If I put -3, it's squared. That means this will be positive. And actually, this is also even exponent. Yes, we can see this is, I can rewrite, if you like, x squared, x plus 1 cubed, and then x plus 2 to the power of -4 means to the power of 4 in the denominator. That means doesn't really matter what number I will substitute instead of x here and instead of x here, because it's the even exponent, I will always get positive value. That means -3. -3 plus 1 is negative number. Negative number cubed is negative. Okay? Let's pick, -1.5, small interval. -1.5, this will be positive, this is positive. -1.5 plus 1 is still negative, and cube is negative. Okay, let's pick, -1/2. That's positive, that's positive. -1/2 plus 1 is actually positive, and cube positive. And let's pick positive number 1, positive, positive, positive. Okay, that's when we can see function is concave down, concave down, concave up, concave up. That means only at -1. At -1, function has inflection points. That means only one inflection point. Okay? And if you probably can be faster than me. I mean, I was trying to like to do the proper way, but what we also have the shortcut. Looking at this even exponent, that's what I was like even pointing out, 2 and 4. This will tell me right away that x to the power of 2, of course, is giving me 0, but at 0, second derivative will not change the sign. Could be both negatives or both positive. Always when you see the even exponents, function, I mean that this function, the second derivative, will not change the sign on left and the right hand side. The sign will stay the same. Doesn't matter if it's negative or positive. For the question, we're not changing the sign, no inflection point. That means only at -1. Only at this one, because it's the odd exponent. That means almost right away we can answer the question. But you can always do the test. Okay, as we know a little bit, it's like increasing, decreasing concavity. That means now we have to look at few more things, horizontal asymptotes, because we know how to find the vertical asymptotes. We're okay with this. But now horizontal asymptotes. In order to find the horizontal asymptotes, we will look at the limits at infinity, like an end behavior. Okay. What I do have something like that. That means this is actually from chapter 1, from the beginning, from the limit concept. That means having a function, a rational function, 3 minus x over 1 minus x, we notice that x equals to 1 is not in the domain. And not always, but most likely, if the number is not in the domain, we have to investigate what is happening at this number. That means we have to compute a limit. And now, computing a limit at this number, because we can see 1 is not in the domain, that means I'm computing limit on the left and on the right-hand side. I've got a number over 0. Number over small number is a huge number. That's means infinity. And as soon as I got infinity, which we call infinite limits, and we do call infinite limits, if you see the infinity, we can call this line, this vertical line, a vertical asymptote. Right? Because this means I don't know exactly the graph, but I know that at 1, on the left-hand side, function will go up. On the right-hand side, function will go down. Okay? We probably have other things to add, but at least, maybe I shouldn't show, will go up and down, because I don't know the other parts. Okay? That we can see is definitely a vertical asymptote. That means, please remember, in order to find a vertical asymptote, we have to find the numbers that are not in the domain and compute a limit. If the limit is infinity, then it is a vertical asymptote. If the limit is not infinity, it's not a vertical asymptote. It's just maybe removable or maybe jump. We have different type of discontinuity. Okay, but now let's focus on limits at infinity, which will be the end behavior, because we have to know how to graph a function and how to end, and like how function behaves at negative and positive infinity. Okay, that means let's look at this function 1 over x. We know how function 1 over x looks like. I can even show you. Okay. Do I have something? I can show you the graph. We remember just the hyperbola in the first and the third quadrant. And first of all, the old stuff, vertical asymptotes. We can see right away from the graph, or looking at the limit, I have to take 0 because it's not in the domain, and I have to find a limit. Limit at 0 from the left-hand side, of course, is negative infinity. This should be right-hand side, is positive infinity. We can see functions going up, functions going down. Okay, that means that's the conclusion. The line x equals to 0 is a vertical asymptote. But now we have to check how function behaves at positive infinity and negative infinity. That means, do you think you can tell me what will be the limit at positive infinity? As x goes to positive infinity, how function 1 over x behaves? Do you know that limit? I hope you can hear me. You can use the chat box. Like, do you remember the really like informal way? 1 over small is big. 1 over big will be small. Yeah? 1 over huge numbers. Of course, it's a tiny number. That means, what is this? What is this answer? Okay, thank you. Thank you for typing 0. And we can even see 0. 0 is the horizontal line, and function is approaching 0. It's getting lower, and lower, but it will never touch that 0, but it's almost 0. And on the negative side, it's below the x-axis, but it's the same situation. Okay, that's mean now. Now it's kind of like opposite. When you're computing a limit at infinity or negative infinity, and we getting an answer, okay? This is of course the y value, okay? That number will give me a line, a horizontal line, and this will be a horizontal asymptote. Horizontal asymptote. But please remember, limit at infinity must be a finite number. And this finite number is a horizontal asymptote. 0 is also a good finite number. If we getting something else, something that is the limit maybe is undefined or limit is infinity, at infinity, then no horizontal asymptote. Okay? That's what we just did. Limit at infinity could be the finite number, which means function is approaching that number, that horizontal line. Okay. The same at negative infinity, exactly the same thing. Okay, and now just what I said, that if the limit at infinity is equal to L, that line L, y equals to L, is a horizontal asymptote. Horizontal asymptote. That's the point is now we have to be confident computing a limit at infinity, positive or negative. Okay, we have to know how to compute the limits at infinity. Okay, a little bit of examples of the asymptote. That we know, I think you have the feeling what asymptote means. It's the line that is, we don't really touch the line, the values of the function, we're not intersecting the line, but you can probably see weird things on these graphs. We have to make sure that this is we have to respect this as an asymptote, but only at infinities. Okay? Let's look at the first one. This is the first one. We can see the blue curve is nicely respecting the asymptotes, right? It's not gonna touch this line. But what happened here? It's intersecting. But doesn't matter. Probably the limit at positive infinity was L. You can intersect sometimes, like you can even see here, and here. We intersecting like whatever we have to do, but probably for 1, 2, 3, 4, the graph 5, the limit at negative infinity was L. That we do have an asymptote only at negative infinity, because we may have, like graph 6 is showing us that we may have different limit at negative infinity and different limit at positive infinity. Okay? That means at positive is -1, at negative infinity is 2. Okay? That means please remember the maximum number of horizontal asymptote is actually 2. Okay? And yeah, this is nice and easy. This is nice and easy. This one is also the second, and the fourth one is easy. Number 3 is a little bit weird. We kind of like intersecting infinitely many times the asymptote, but what this function does is kind of like a snake. I always call kind of like a snake. It's kind of approaching, okay? It's like oscillating between that line. That means I don't know exactly what's the formula for the blue curve, but I'm assuming the limit at infinity is L. It's a finite number. Okay, because function is, it's a weird way to approach L, but it's also an asymptote. Okay, that's me now. Let's look at some limits. We will start computing a limit at infinity, but we have to just understand this, which we kind of did. 1 over x was similar. That means if we have this function, okay, like the r is just the positive, like a positive number. That means having a function 1 over x to the power of, like additional number, to the power of r, okay? And this form, this function, will behave at infinity like this, will be always 0. That means, because what I see, I kind of see this as a 1 over big number, like x is big, right? And then I'm even taking to the power of 1, 2, 3, 4, like any number. Okay? That means 1 over big is always small. Okay? That means that's what we have to, of course, it's really informal, but this means kind of like 1 over infinity, 1 over a huge number is small. Small for us is 0. If it's the other way, 1 over small, which that was chapter 1, and that's for the vertical. 1 over small is big. Okay? That means you can adjust, you can always apply this to the limits. Okay, that means, remember this, that 1 over x to the power of 1, 2, 3, 4, 5 at infinity is always 0. Okay, that means now let's see. I can show you a few things, and of course, as always, I will tell you a little bit of shortcuts, but still we have to kind of understand the algebra behind. Okay, that's, let's start. Example number 1. That's, what do you think? What is this limit? 1 over x minus 5 at infinity. How this function behaves at infinity? We can think like, okay, infinity, I know that infinity is not a number, but if I will think that this is infinity, huge number like x minus 5, it's still a huge number. That means 1 over big number is small, 0. Okay? That means this limit is 0. But what we have, we do have like a few steps, the algebra steps to get the answer. That means I will look at this function. On the top, I have nothing to do because it's just 1. But in the denominator, I have to find a leading term, which is x, and I have to factor out. That means, let's see. Okay? I did factor out x. Distributing back, x times 1 will give me x. X times 5 over x will give me negative 5 back. Okay. But now what I see my, like, just the limit that I showed you on the previous slide, like a reference limit. 5, like a number, doesn't really matter what's the number, but one number, the constant number over a huge number is 0. Okay? And then 1 will just stay, but 1 over x is another, like 1 over big number is just 0. That's what we can see. Look, doing this, we're really creating, I can come back for a second, we're really creating this. Okay, 1 over big is small, or 1 over x to the power of a number. Okay, that means I have this, 1 of course is the constant, and I end up with 1 over x, 1 over big is small, 0. Okay, now let's look at this function. Limit at infinity of the rational function 2x minus 1 over 4x squared plus 5. Do you think you can guess the answer? Of course, the educated guess, not really the wild guess. 1/2. Okay, and not really, but I can tell you in a minute, probably in 5 minutes. In 5 minutes, we will use that. We will use that trick. Okay, that means yes, it's still 0. Okay, because what's happened? I will do exactly the same thing. I have rational function, which means polynomial on the top, polynomial on the bottom, at the bottom. I will take leading functions, okay, which is x on the top, x squared in the denominator, and I am factoring out. Okay, I factor out x. Of course, you can check distributing back, you will get my original function, and the same in the denominator. And the same thing, this is 1 over big, 0, 5 over big, 0. And 4, 2 and 4 doesn't matter. But now what I have x over x squared. I can still simplify, and I will get 1 over x, and 1 over x, of course, is 0. Okay, and let's see one more. This one is at negative infinity, but it is important to notice this, but at the moment, let's see what we have. Okay, again, I have rational function, and I will take the leading function from the numerator. I will factor out, and I will factor out the leading function from the denominator. That means x cubed is the leading function, and x to the power of 4. I factor out. I hope you can, yes, you can do this, because distributing back, you will get the original function. And then let's see what's happened. This is 1 over big, small. This will also simplify to 1 over x, 0. 2 over big, small. 1 over x after simplifying 0. And the same thing will happen. 5 and 1 is a constant, but x cubed over x to the power of 4 will give me 1 over x, which means is 0. That's mean you can see all of the 3 examples where the limits at infinity of the rational function, and what we notice. I will ask you one thing. Look at the first question. Having 2 polynomials, which degree, I mean denominator or numerator, had higher degree? Can you tell me, like, who was winning, denominator or numerator, in terms of the degree of the function? Denominator, of course, because it was x to the power of 1, just the constant. Okay, what about the second example? Who was winning, denominator or numerator, in terms of the degree of the function? Yes, we can see again denominator, right? Because x to the power of 1, x to the power of 2, denominator is winning. X to the power of 3, x to the power of 4, denominator is winning. That means looking at the whole algebra, you will probably notice that always, I will end up, I can cancel out everything, but I will end up with the x without canceling that x in the denominator. Yes, we can see 1 over x, 1 over x, 1 over x. That means if the denominator is winning, always the limit will be 0. Okay, that means, please note, that means that's the good news, is you don't really have to do all of this stuff. I mean, we have to understand the arithmetic and algebra behind, but you always can think, okay, I can cancel out everything, but the denominator will always give me x, and x is infinity, big number. That's mean now, can you tell me the limit of this function? Limit at infinity of 3x to the power of 5 plus 6x to the power of 4 minus x plus 10 over x to the power of 7 plus 8x squared minus 3. Can you tell me that limit? Oh, we do have, of course, yes, thank you. Of course, it's 0. That means one more comment. Looking at the limits at infinity, please remember, we're only talking about the limits at infinity, the end behavior. Limits at infinity, the only important part is a leading function. Okay, because you can see, I will factor out the leading function, rest of the functions goes to 0 anyway. That means only the leading function. And this one is 3x to the power of 5, x to the power of 7. Denominator is winning, is 0, always. Okay, that means we can only focus on the leading function. Leading means the highest degree. Okay, and one more thing, all of the limits were 0. That means we can make also the conclusion that we just learned, that the line y equals to 0 is a horizontal asymptote, actually, for all of them. Okay, even for this one. Okay, y equals to 0, that's too big, is a horizontal asymptote. Okay, that's another conclusion. Okay, let's move on with the next kind. What about this one? Limit at infinity of 3x plus 5 over x minus 4. Now we can see we're focusing on the leading function, which is 3x on the top and x in the denominator, and they actually are the same. Yeah, none of them is like winning in terms of the degree. X to the power of 1, x to the power of 1. That's what do you think? What will be the answer? Do you think you can guess? It's now the answer is 3. That's what we will do. We will do exactly the same what I did on the first type. I will factor out that leading function x. I'm factoring out x, I'm factoring out x. And then this goes to 0, this goes to 0. And what stays? 3x over 1x. I can cancel out x because it's the same function. That means factoring out, I will always cancel out that common factor, which is identical. And the only thing that matters in this case is the leading coefficients. That means if the degree is the same of the polynomial from the denominator and numerator, the limit at infinity will be the ratio of the leading coefficients, 3 over 1. Can you tell me that limit? Limit at infinity, 2 minus 3x squared, 5x squared plus 4x in the denominator. It's negative 3 over 5. Thank you. Because the leading function is this one and it's this one. Of course, I did change the order because I don't want you to think that the leading function is the first function. No, it's just the function with the highest degree. Okay? That means, of course, I did my algebra, but if you know the answer right away, you can put the answer right away. This goes to 0, this goes to 0, and x squared, I can actually use different color. X squared is gone, and what matters? Negative 3 and 5. Okay, and this one, can you tell me that limit? 4x squared, and the rest of the stuff, 7x squared, and the rest of the stuff. Limits at infinity are not, I can say we don't really care for the rest of the stuff, just the leading function. Yes, thank you for the answering. It's 4 over 7. Of course, this will go to 0. This is the same function. Okay, and that's the answer. Leading coefficient 4 and 7. Okay, that's the conclusion. If the degree is the same, always remember to take the ratio of the leading coefficients. That's me now. I have one more function on this slide, and it's kind of like an exam type. Who can tell me the correct answer? And even if you're watching, you can also maybe pause the video, not hearing the answer, okay, and try to answer this. Okay, what is this limit? Limit at infinity, and the function is 4x to the power of 4 plus 5 over x squared minus 2 times 4x squared minus 1. What do you think? What is this limit? Nice exam type. Okay, I see one answer. Can you all try to answer? Even if it's wrong, it's fine. I know that it's not. easy sometimes. Yeah, okay, another one. Okay. Okay, that means yes, this is the correct answer. The answer is 1. Because what we will do, I will only focus on this, as I said. And if I will distribute everything in the denominator, that will be my leading. This will be my leading function. 4x squared times x squared is 4x to the power of 4. And the rest of them will be with the lower degree. Okay, that means identical function, 4 over 4, of course, is 1. I can possibly write 4 over 4. Okay, that means this is nice. Of course, additional thing, but this is nice exam type or the quiz type question. Okay, and one more thing. All of these answers, all of these numbers are the horizontal asymptotes. Okay, that means function at positive infinity. Let's maybe analyze the first one. Y equals to 3 is a horizontal asymptote. Okay, at positive infinity. I still don't know how function looks like because I really have to check concavity, but if the function is concave up, we'll approach that line 3 from above. If function is concave down, we'll approach from below. Okay, because we have to respect, we can't intersect a line, horizontal line at infinity. I can intersect somewhere here, but not at infinity. Okay, and the same applies for all of the other finite numbers. Okay, let's look at the next page. This one is still similar type, it's not a new type, but I will play with the degree of the function. Okay, that's mean, what about this limit? What do you think? You should answer this question if you really understood the previous slide. Limit at infinity and function is x plus 2 over square root of 9x squared plus 1. That's mean, what do you think? What is the degree of the denominator? Right? What's the degree of the denominator? And you see, we do have, looks like x squared. It's 1, right? Because it's x squared, but we're taking the square root. That means it's actually x. Okay? And what will be the coefficient of this function? I mean, I did the same way, I factor out, but we can, of course, we can do the shortcut. This is x, and we will focus on this one because at infinity, limits at infinity, we're focusing on the leading function. That means this is x. Okay, this is x. I will erase this. Give me 3x. Okay, x, the same degree, the ratio of the leading coefficients, 1 over 3, 1/3. Okay, because that's what I have to look. I have to look at the leading terms. But what I did the same thing. I factor out x, I factor out x squared. I mean, still keeping the square root. And then, oh, I have my answer. But actually, yes, this is 0, this is 0. And x and the square root of x squared, if x is positive infinity, this is the same. And square root of 9 stays, which is 3, 1/3. Okay? We have to be still really careful because what I am doing this simplification. Square root of x squared, it is x, only if x is positive. Okay? Or I can say if x goes to positive infinity. And we have to be careful with these limits. We have to be careful with negative infinity. But let's see. I have another one. That means, can you answer this question? Limit at infinity, 4x squared under the square root and 8x. Yes, that's the battle between these two numbers. That means, can you tell me what is the degree of both of the functions? Square root of x squared is 1, right? And of course, in the denominator, I don't have to even ask you, is 1. That means the only thing that we have to do, we have to take the ratio of the leading coefficients. That means, what is the coefficient? Okay, I do have. What's the coefficient is definitely 8 in the denominator. Can you tell me the coefficient from the numerator? It's 2. Yes, thank you. Okay, that's mean you know. The answer is 1/4. Thank you. That's good. Because we have to take the square root of I mean, we're looking at this and this, and we have to just simplify, which will be 2x over 8x. And x is gone, just 1/4. Okay. Now what I have, now we have to be careful because now I have exactly the same function, but I am looking at the behavior at negative infinity. Okay, that means this one, before we solve, I would like to show you this and make sure that you know the difference. As I said, like before for the first one, square root of x squared, I can simplify nicely for just for x if x is positive. But if x is negative, okay, I can't just put x. I have to make that x negative, which means I have to make it positive, which I will add additional negative. That means, for example, like, what about square root of negative 5 squared? Can I just copy this number, negative 5? Of course it's wrong, right? Everybody knows that it's wrong, because I can compute this, negative 5 squared is 25, and actually square root of 25 is 5. That means, but I will not do this, of course. That means what we will do, if this number is negative, I can still copy this number, but I have to make it positive. That means this is this extra negative that ironically is making the expression positive. Okay, that means please remember, square root of x squared, if x is negative, or in our case, if x goes to negative infinity, that's the same thing. Okay, always we have to put negative x, because it's actually, as I said, ironically, it's positive expression. Negative and negative, we can see negative 5 and negative, negative 5 and negative, it's actually positive. Okay, that means now, sorry, I have some, what will be the answer? This is not a problem because I have nothing, I have no negatives, I have no square root, I can copy 8x. But this one will be square root of 4 and square root of x squared, if I would like to make the shortcut. That means this is still 8x, this is 2, but to simplify square root of x squared at negative infinity, I will do this, right? That means the answer is actually just opposite sign, not 1/4, negative 1/4. That means please be really careful for these signs. Okay, and I have a few more. Okay, what about this one? Actually, I do have, I have lots of them. Okay, 12, question 12. Do you know the answer? Because question 12, 13, that's the only two that is at positive infinity. The rest of them are at negative infinity. Okay, that's when we have to be a little bit careful. Actually, one more thing. How would you simplify? Because I would like to make sure, how would you simplify x to the power of 4 at negative infinity? Because I would like to, let's say x is negative. Okay, x is negative. That means what will be the answer? Positive or negative? No, nobody's answering. Because what we have to be really careful, we still have negative, okay, like I can write maybe this way, x squared, and actually everything squared, okay, because this is kind of like a double squared. That means the second square is making everything positive. That means even if x is negative, I can move this down. I will still simplify the expression inside as a negative x, but what I have, I'm still squaring. That means squaring x or squaring negative x, I have x. That means square root of x to the power of 4 will actually give me x, because I'm respecting my definition, my property of the absolute value, but I'm squaring one more time. That means that's also quite helpful. Okay, and let's see. Okay, I can show you all of them. Okay, that's in 12 and 13, we shouldn't have a problem. Do you think you can tell me the answer for 12? What's the answer for 12? We do, we have 1/4, the answer, let's see. We have 5th root of x to the power of 5, which will give me x, and this is x. Okay, that means just the 5th root of 32 over 8. And I believe this is 1/4, really good. Because 5th root of 32 is 2, 2 over 8 is 1/4. Yes, really good. Okay, okay, now what about 12a? 12a is at negative infinity. You see, it's at negative infinity, but what is the good thing? The good thing is we have odd. Okay, we do have the odd root. That we shouldn't be worried for any negatives. Okay, I can also say this is the x, because I will cancel out both of the x's. I don't have to make it. I can have actually negative. The fifth root could be a negative number. Okay, that means this will be exactly the same answer. Okay, that means that's this. Okay, what about 13? What about 13? We do have still is at positive infinity. That we should be okay. We have cube root of x to the power of 6, which will give me x squared. Yes, because we can cancel out. That means the same degree. That means since this is the same degree, I will only have the ratio of the leading coefficient. 2 over 4 is 1/2. Okay? Or 14 is interesting. Okay? Because we do have square root of x squared at negative infinity. That means this will give me -4 and 2x. -2. Okay, because that I should actually write it's the same way. Square root of 16 is 4, but square root of x squared is actually -x. And it's just 2, -2. Okay, that's important. I can make it bigger. Okay, and I can leave the questions for you, but maybe, what about this one? 15, let's do one more. We have square root of x to the power of 6 at negative infinity. That means, let's think, square root of 9 and square root of x to the power of 6 and x cubed. This is 3. And now, how can I simplify square root of x to the power of 6? I can write, and it's at negative, okay? That means I will write square, and 2 times 3 is 6, right? Am I right? Yes. That means now this must be definitely negative. And I will keep that cube. And that we can see, we have to be really careful with this. I can make the same cube. Because making this negative x, I am respecting the definition from the previous slide. And this will give me still negative x cubed, because negative to cube is negative. And the final answer is -3. I'm sure you can see the answer right away, but I really wanted to show you the steps. And that means always is important what power stays. If this will be even power, everything will be positive, even if it's at negative infinity. Yeah, that's my point. Okay, let's move on, because we do have, okay, I do have few limits like that. That means that's totally different. but still at infinity. I just want to let you know that sine of x at infinity is not really defined. Okay, that means because we know how sine function behaves. Sine is simply like 1, -1, 1, -1. Will really oscillate. That means function sine doesn't really go to one direction at infinity. Okay, that's different. Sine of 1 over x, 1 over big number is small. That means the answer is sine of 0 is 0. Okay, and actually this one is Math 141. We can wait for the next semester. This was in the chapter, but I kind of like see now that this is more for Math 141. We will not investigate this one. Okay, that means remember number 18, remember number 19. And then I have few limits, like at infinity, which we will not get a finite number. We will simply get infinity. This means in terms of the horizontal asymptote, function will not have horizontal asymptote. Okay, that means let's see, for example, x cubed. How function x cubed behaves at infinity? Of course it's infinity. How function x cubed behaves at negative infinity? Of course negative infinity. We know the graph. Okay, this will go to positive infinity, will go to negative infinity. That's x cubed. Okay, and actually also, let's leave this one. It's also more like Math 141 because it's infinity. Yeah, let's look at this actually for a second. X squared minus x. It's, if I will do direct substitution, it's infinity minus infinity. Right? And this is a big problem. I mean, it's not a big problem, it's the solved problem, but we do have a problem with this expression at first. Okay? And the same for this one. And this is definitely a topic for later. Okay. If you're going to take Math 141 the next semester, I will explain you this next semester. Okay, let's see. Okay, a little bit of rational function with the same idea. That's me now. Looking at this and knowing all of these other types before, what do you think? What is the limit of this function? 2x cubed and the rest of the stuff, x squared and the rest of the stuff. That's what we will get after simplifying the leading terms. Oh, nobody can answer. I think too many limits. We will get 2x, right? I can simplify 2x cubed over x squared is 2x. And since after simplifying, I will get, let me keep my limit, I will get just 2x and something else, which I don't really care for the rest of the stuff. X is infinity, the limit will be infinity. Because I did end up with x, not in the denominator, just simply x. Okay, and what about this one? Can you tell me 26? X squared and x. Infinity, because but now let's see one small mistake. For x squared over x, I will end up with x, but for x. But now let's see what is the limit at. It's at negative infinity. That means 4 times a negative big numbers will give me negative infinity. Okay? Again, it's infinity, but we are on the negative side. That's also, please make sure that you looking at this negative or positive. Okay, 27. Who can give me the answer for this one? This one, 27 is tricky, lots of negatives around. A nice exam type question. I can circle for you leading. Okay, that's mean, what is the answer? Positive infinity or negative infinity? Of course, that's my point. It's positive infinity. I think it's positive. Let's check. Negative x squared over 20x. I can simplify negative x over 20. And the limit is at negative infinity. If I substitute negative big numbers and another negative will give me positive. Yes, thank you. Positive infinity. Really good. Okay, that we can see. This is the types like limit at infinity, and we got infinity. And this means that these functions doesn't have a horizontal asymptote, yeah, because we're not getting a finite number. Okay, that means you can definitely solve this. Okay, that's what I think we find with horizontal asymptotes. I will skip this one. Okay, that means what I have. I still have this section. That means let me go, yes, not really fast, but not really slow too. That means I will cover this section because this is just the summary. We almost know everything. Okay, I think we're missing 1 or 2 items, but I can show you. And again, my announcement from the beginning of the section about section 3.7. 3.7, you still have a quiz, self-assessment, and the weekly quiz, which is the extra credit. And what I will do, I don't want to keep the session long. I will do exactly the same session, but I will run probably after this one. I can definitely put the my problems, which are solved problems, but I can still run like a half an hour session for optimization. Okay, that means you can check the session later on Canvas. But now let's finish 3.5. That means 3.5. We will talk about the summary of the curve sketching, and this is like the guidelines, the points. That means having a function. Okay, I will ask you to sketch the graph, or maybe to pick the graph, because of course all of the questions are multiple choice, or maybe pick some points. And what we will have to do, always, in order to sketch the graph, having a function, we have to find the domain, x-intercept, y-intercept, and then we can see horizontal, vertical asymptote, horizontal asymptote, or eventually slant asymptote. That means this is one thing that we're missing, and I can show you in a minute. Okay, all of these points are related to function. Now we can see the middle part. Critical numbers, increasing, decreasing, local minimum, local maximum. This is related to the first derivative. And then concavity, inflection points. This is the second derivative, testing the second derivative, and sketching the graph. And another thing that is new is the symmetry. Okay, that's what we'll do. Let's cover slant asymptote and the symmetry, and then let's take only one function and go through all of these points and let's finalize the function and the computation with the graph. Okay, that's the plan for the next maybe 20 minutes, and we will be done. Okay, what I have. Oh, actually, I'm starting with the symmetry. That means you probably remember from college algebra that we do have 2 types of function. We have an even function, and we have an odd function, which I have on my next slide. Okay, even and odd. Let's come back to even. Even function has the symmetry with respect to the y-axis. That means if we will if I will bend, I can't bend my laptop, but if you will draw a function on the paper and bend it along the y-axis, it will be the mirror image. Yeah? That means the reflection, which means all of the values for positive x, like let's say, are exactly the same like for the corresponding negative. Okay? That means values for x are exactly the same like values for negative x. That means that's the property of the even function. And we can see even, it's easy to recognize, right? X to the power of even number, 2, 4, 6, 8. They will be always symmetric with respect to the y-axis. Or absolute value, because absolute value of 5 and negative 5 is the same number. Okay. And cosine, one of the trigonometric function cosine of x is also an even function, okay? Which you probably remember, cosine of x is the same like cosine of negative x. This is, it's not really cosine, but if this will be even, it will be cosine. Okay, that's the property, that's how we have to check if the f of x is the same like f of negative x. Okay, and now we do have odd function. Odd functions are a little bit different because we have to satisfy this statement, this equation, and what this means in terms of the rotation. Function is symmetric with respect to the origin. I know that is probably not easy to imagine this, but what this means, if I will take a curve and if I will rotate 180 degrees, I will get the same function. Okay? Yes, and one of the easy explanation is looking at the x cube. X cube is really an odd function. And we can see, it's kind of like I can't say the mirror image, but it's kind of like a reflection with respect to the origin. We can see the first and the third quadrant are almost the same. They are rotated, but they are the same. Okay, and now the equation means that value, for example, for 2 is 8. Okay? But for negative 2, if I put negative in front of the x, I will have negative in front of the y. Yes, we can say that's the equation. F of x, that means f of 2 is 8, but f of negative 2 will be negative 8. And we can say, hang on, too many. That's negative, and this is my negative. Then I can say they are the same. Okay? Because f of negative 2 is negative 8, and I have to put negative to make them equal. Okay, that's how we can check. We can simply take the equation and check if the f of x is the same like f of negative x. Okay, that's the symmetry. And we're not going to talk about the periodic function. Of course, the periodic functions that we like to know, it's the sine, cosine, tangent, cotangent, not even secant, cosecant. But the periodic function means that the function simply repeats like every other number. Yeah? And this number we call period. That means every in this case is p. Every p is the same situation. Like every 2 pi for the sine function or the cosine function. Or every pi, the situation is the same for tangent of x. But I will not ask to test the periodic functions, no. Okay, now the slant asymptote. We know that function can have a vertical asymptote. We know how to find this. Horizontal asymptote, yes, we spent an hour to computing limits at infinity. Or if a function doesn't have horizontal asymptote, could be the case for the slant asymptote. That means this is just the definition, which we of course understand, having a function, blue function, and the line. In order to name this line an asymptote, we can see as soon as the function is approaching this line at infinity, the vertical distance is getting smaller and smaller because the curve is almost like getting closer and closer, almost touching, of course, not touching, but is approaching a line. That means this line, if the vertical distance between them is 0, it's getting almost 0, then we call this line a slant asymptote. That's what we have to have, the difference between the function, which is blue dot, let's say, and the value on the line, mx plus b. That means the difference between blue minus red must be 0. Of course, as x getting bigger and bigger. Okay. And now, how can we identify? I can show you. Okay, because sometimes we have the function easy to identify, but for you, I will make a little bit easier, and the only function that I would like you to recognize that has a slant asymptote will be a rational function, okay? That means, for example, I can give you function 2x cubed plus x squared minus 1, and let's say x squared plus 2, okay? That means this is rational function. First of all, can you tell me what will be the limit at infinity? What's the limit at infinity of this function? We just finished this topic. Who can tell me? rational function, ratio of polynomials, check the degree. That's what is the limit at infinity. It's infinity, right? Because it's 2x cubed over x squared, it will be infinity. That means definitely this is telling me that function doesn't have a horizontal asymptote. Okay, but if doesn't have horizontal asymptote, this could be the case for the slant. And this is a case for the slant asymptote. Because what we will have, you read probably my first statement, having a rational function, okay? We're looking for the degree from numerator and denominator. And now, if the degree is one number, just one number more in the numerator, then it's always the case for the slant asymptote. Okay? That means if the numerator is winning by 1, okay, we can see 3 and 2. And yes, this is the case. That means if the degree of the numerator is 1 more than the degree of the denominator. Please remember, no horizontal asymptote, of course, but this is the case for the slant asymptote. Okay? And now, how can we find the slant asymptote? We simply have to take this function from the top and divide by the denominator. Just the long division. Okay, let's do it. I don't know, I picked a random function, but let's try. That means let's find the slant asymptote. I will take 2x cubed plus x squared minus 1. And actually, I can put plus 0x minus 1. Because we remember, we have to have each term in order to divide. And I will divide by x squared plus 2. Okay, long division. 2x cubed divided by x squared will be 2x. Now I have to multiply back 2x times x squared and 2x times 2 and subtract. That means 2x times x squared is 2x cubed, and I will be subtracting 2x times 2 is 4x. Oh, I have to be careful. I have to write here 4x, but I will be subtracting. Okay, this is gone. I can drop down this one, and 0x minus 4x is simply negative 4x and minus 1. I can drop this down. Okay, now I think I can still divide. Leading coefficient, leading terms only. X squared divided by x squared is just 1. 1 times x squared is x squared, but I will be subtracting. 1 times 2 is 2, but I will be subtracting. Okay, this is gone. I am dropping this. Negative 1 and negative 2 is negative 3. Okay, now the degree is less than my divisor. Then this is simply the remainder. And on the top, I have the quotient, and the quotient is the slant asymptote. Okay. This is my quotient, 2x plus 1, and this will be actually a slant asymptote. We can see mx plus b, slant asymptotes. Okay. That means simply the long division. Okay, let's maybe do one more. Actually, I can leave this one for you because I have a multiple choice. That's the question that you might see. And let's see, find the slant asymptote of the function. Of course, we can definitely see that this is the case because it's x squared and x. The numerator is winning by 1. Okay, you can try to do, and I will do, and maybe we can compare. Okay, it's x squared plus 3x plus 2. Oh, this one is much, much easier than I just did. I can tell you always that exam questions are easier than any other sample tests. Okay. Okay, let's divide. X squared divided by x is x. Now I will multiply back x times negative 2, but I will subtract. X times x is x squared. I just don't like this line. Is x squared, but I will subtract. X times negative 2 is negative 2x, but I will subtract. I'm changing the sign. This is gone. 3x plus 2x is 5x. and dropping down 2. I can still divide. 5x divided by 5 is 5. 5 times x, 5x minus 5 times negative 2 is negative 10, but I will subtract. Gone 12. Okay? I don't even have to. As soon as I have my quotient, 2 terms, I can say that's my slant asymptote. Okay, that means this is the answer. That's the slant asymptote. Slant asymptote. Okay, that's a nice question. Okay, that's I think we okay with everything, the symmetry and the slant asymptote. But what I was planning to do, I was planning to take one function like this one. Let's maybe do, because that will be, and go through all of these points. Okay, but let's see something. The question is, sketch the graph of the following function, and the function is 2x squared over x squared minus 1. Okay, and you can probably notice that I am providing a first derivative and the second derivative. That means if you end up having this question, okay, on the test, I will definitely provide for you, of course, a function, but also the first and the second derivative. Because what's the point is? The point is, let me switch the slide for this one. The point is to answer these questions correctly. That means in order to answer these questions, we definitely have to have correct derivative and correct the second derivative. Because if you will make the small mistake in your first or second derivative, this section will be wrong, this section will be, like almost everything could be wrong. And I don't want you to have wrong formulas. I want you to focus on the question, having the correct formulas. Okay, that's the reason that for this type of question only, I will give you everything. I will provide the function, first derivative, and the second derivative. Okay, let me maybe come back for this slide because I just want a little bit of space. That means first of all, what we will do, we will find the domain. Okay, domain. Looking at this function, okay, I see the domain are all of the numbers except -1 and 1. That means 1 and -1 are not in the domain, right? Correct. Okay. Actually, maybe I can squeeze everything here. Okay, if I will have not enough room, then I will come back to this slide. Okay, that means domain, you can probably write that. 1 and -1. Okay, now the x-intercept. X-intercept means that y is 0. Okay, I can maybe, x-intercept means that function is 0. Function is 0, fraction is 0, if the top is 0, which means x is 0. Excellent. And now the y intercept means that x is 0. That means I am computing my value, okay, and substituting for x 0. How can I do this? Let's do this way. Okay, but of course it's 0 over -1, of course it's 0. And you probably notice, okay, y and x. You probably notice as soon as x is 0, y must be 0 because it's the point 0, 0. Okay, that we do have x and y intercept. But please remember, for x intercept, y is 0. For y intercept, x is 0. Yeah? Not always is 0, 0. Please remember this. Okay, that we do have 0 and 0. Okay, now, can you tell me the vertical asymptotes? Do you remember? The vertical asymptotes are the numbers that are not in the domain, right? But, however, we have to check if it's infinity. But we can see I will never cancel this x squared minus 1. Because if you can cancel out, then you're getting a finite number, and then it's the removable discontinuity. But I will never cancel out x squared minus 1 with 2x squared. That means this line and this line are the vertical asymptotes. Okay, now question for you, horizontal asymptote. Do you think this function has horizontal asymptote or slant asymptote? Do we have slant asymptote? Maybe I can ask horizontal. Yes, that means no slant and horizontal. Horizontal lines are y equals 2. That means what is the horizontal asymptote of this function? True, thank you, because the limit at infinity is 2. Really good. I can maybe come back. Horizontal asymptote is simply a limit at infinity. And you actually learn something I'm really happy is 2. That means this is a horizontal asymptote. Really good. Okay, 2. Okay, that's we done with the function. Now we have to investigate the first derivative. Okay, looking at the first derivative, who can tell me a critical numbers? Who can tell me critical numbers? Can you see the critical numbers? Do you remember zeros from the numerator and zeros from the denominator? That means critical numbers are if the derivative is 0, derivative is 0, if this fraction is 0. This fraction is 0 if the top is 0. Where can I write? Okay, can I write here? Okay, let me write here. Derivative is 0 if negative for x squared minus 1 squared is 0. Fraction is 0. Okay, that means x equals to 0 is definitely in the domain and is critical point. However, critical point is the points that derivative is undefined. And what we can see, derivative is undefined if the denominator is 0. Okay, we also remember this. Derivative is undefined if the denominator is 0. But denominator is 0 if x is positive and negative 1. That means normally I will place this as a critical numbers, but they are not in the domain. That means please do not list them as a critical points. They are still important points. We can see they are the asymptotes, but they are not critical points. Okay, that means only 0. Okay, but what I have to do, now I have to test the first derivative for the increasing, decreasing, local minimum, maximum. That's mean what I will do. I will put 0, that's my critical point, and I will still put an asymptotes. I mean the numbers that are not in the domain. And now the test values. If I will put negative 2 here, I will have positive. If I will put negative half, I will also have positive. Positive half, or negative, because it's negative 4 and negative. That means function is increasing, increasing, decreasing, decreasing. Only at 0 is a local maximum. None at x 0. Okay, we can see maximum. And increasing, of course, is from negative infinity to negative 1, from negative 1 to 0, from 0 to 1, from 1 to infinity. We have to exclude the asymptote. Okay, nice graph. And now, that means this was the derivative. Now the second derivative. Looking at the second derivative, of course, we still have this negative 1 and 1 problem. That means this will be not an inflection point, but will be an asymptote. And we need a numbers that the top is 0. But we can see x squared plus a number, this is never 0. That means we will probably have no inflection points. Okay? But in order to test the second derivative, I still have to put negative 1 and 1 only, because that's the zeros from the denominator. They are not in the domain, but they are still important. Okay, and let's take the test value. Negative 2. substituting -2 and -2. Now I have to be careful because 12 times this will be positive. -2 squared is actually positive. Positive minus 4 minus 1 is positive. That means this will be positive. Okay, this is nice and big interval. I can pick 0. If I put 0, I have -1 cubed, negative. And if I will put big number, positive. That means function is concave up, concave down, concave up. Okay, that we do have an intervals. Concave up is from -infinity to -1 and from 1 to +infinity. And concave down between the asymptotes. Okay, symmetry. We can see that the function has only even exponents. Definitely f of x will be the same like f of -x. You have an even function. Okay, and now what we have to do? We have to put all of the information together and get the graph. Okay, as we can see, function is increasing. We will have local maximum at 0. We have function concave up, and concave down. We do have a horizontal asymptote too. That's what I have. I do have the graph. I can show you. The graph looks like that. Yes, we can see an asymptote, horizontal, 2 vertical. Function was like concave up, concave down. Okay, and then function was increasing and increasing here, and then from 0 was decreasing and decreasing. And that's when you can definitely, you can get this graph, combining all of the information together. Okay, that's mean that was kind of like a summary of everything. Okay, that's mean I will finish the session. As I promised, the short session of optimization will be placed tonight on Canvas. Please watch how can we solve these problems. And of course, practice this. I can also show you, because these slides I will post on Canvas, I have more problems. Like I have another function, but I have only graph. I have another set of functions and I have graph. I have, oh yeah, like this one, but you can only look at the function, derivative, and the second derivative. And you can try to go through all of these points and get the graph. I have another set of functions and the graph. Another set and the graph. Of course, I have lots of graphs. You don't have to do all of them, but if you like, you can try to go through. Okay? But again, the exactly type of the question I'm asking are placed on the sample tests. Okay, do not miss any question on the sample test. That will be your good practice, excellent practice, even for this week. Okay, you can pick the questions, but please remember, create the real examination settings and take the test. Then you will see everybody will score above 90. Okay, thank you for today, and watch Canvas for more sessions. Okay, any question, post on the discussion board or email me and I can try to help you. Thank you.